All right. Hi, everybody. It's Brian again. Just a few short things for this week's module. We're still doing linear regression, but now we're going to look at some hypothesis testing issues. There's not a lot more that we need to learn how to do in StatCrunch, but I'll just show you some more stuff from the statistical output. So we're going to continue to see problems like this. We have a data set here, x variables and y variables paired together. I'm going to open this data in StatCrunch. We're going to do a little bit of analysis in there. All right. So as we've done many times before, we're going to do a linear regression, a simple linear regression, since we only have x and y, and just click compute. Now, we're going to look at this in a slightly different way now. We're not going to just look at this at the output at the top, but we're going to go down to the parameter estimates. So throughout all of statistics, we're trying to do inference about parameters that we can't see but we know are there, right? Like we don't know the population mean. It's just something we can estimate. Well, if there is a linear relationship between the x and the y, then there is a slope and there is an intercept. We call those beta 0 for the intercept and beta 1 for the slope. Okay, so that's what the betas are. They represent the true values that actually exist out there in the universe. They're fixed, but we don't know them. From data, though, we can estimate them, and we estimate with B0 and B1. We use English letters as our statistics to approximate or estimate the Greek letters, which are the parameters. So, but the numbers are the same. The intercept is going to be the B0, so that's negative 3.581, and the slope 2.25, rounded up, 2.56. The standard error is going to be also given our output. The standard error is an estimate for the standard deviation of the error term, which is there's something that we're not capturing in our model. If our model was perfect, we wouldn't have any difference between our line of best fit and the actual data points. But there is some sort of error. It could be measuring error. It could be other factors that aren't in our model. Whatever it is, we can estimate the standard deviation of that error, and that is the error standard deviation, standard error. That's what it's called, 1.3753. I'm just going to copy it right over to my answers. If the residuals are normally distributed, so the standard error of beta 1, the standard error of B1, for each of these estimates, we're given a standard error right next to it. So for the slope, the standard error is right here. I'm just going to copy, it's 0.33, but I have to round it up to 0.332 to get three decimal places. The standard error is what we're asked for. When I say S with a little subscript B1, remember B1 is the slope, so the standard error of B1 is that number. Check it out. Now, assuming the residuals are normally distributed, test that the null hypothesis of beta 1 equals 0 versus the alternative beta 1 not equal to 0. So in this statistical output, you're given standard estimate, standard error, as well as this other stuff. This alternative is specifically this. If you were to form a hypothesis test and say, okay, for the null hypothesis, let's say this slope, let's say it's 0, which is like saying there is no linear relationship between x and y. It's just x doesn't have any real bearing on the y value. That's what a 0 slope would mean. And the alternative is that, no, the slope is not 0. It's some number that's not 0. That's what this alternative means. And then it does the hypothesis test by which I mean it calculates a t-statistic and it gives a p-value. And so that p-value for the test is right here. 3 decimal places is very easy, 0.007, right? I round it up to 0.007. So what would that p-value mean? That's a really low p-value. It's less than 0.05. It's less than almost anything, right? It's very, very, very small. We would reject the null hypothesis. There is sufficient evidence to conclude that a linear relationship does exist. That's what rejecting the null hypothesis means for linear regression. We're rejecting the hypothesis that there is no linear relationship.